In this video, we walk through a complete machine learning pipeline using the famous Iris dataset. Load data, split into train and test, build a KNN model, K equals 3, make predictions, evaluate accuracy, and predict a new flower. Perfect for beginners in machine learning, data science, and Python. Let's understand how K-nearest neighbors, or KNN, actually works. First, in step 1, KNN simply stores all the training data. Next, step 2 is choosing K, the number of neighbors we look at. If K is small, like 3, the model is very sensitive to noise. If K is larger, like 5 or more, it becomes smoother but less precise. So basically, K controls the balance between sensitivity and stability. In step 3, we compute the distance. For a new data point, we measure how far it is from every point in the dataset. The most common method is Euclidean distance, basically the straight line distance. And this works even when your data has many dimensions. In step 4, we find the K nearest neighbors. We sort all distances from smallest to largest and simply pick the K closest points. So at this stage, we've identified the most similar data points, and we're ready to use them to make a prediction. The final step, making the prediction. For classification, we look at the labels of the K nearest neighbors and simply count them. Whichever label appears the most, that's our prediction. So if we have apple, apple, and orange, the final answer is apple. For regression, it's a bit different. Instead of voting, we take the average of the values. So if the neighbors are 10, 12, and 14, the prediction becomes 12. So in summary, KNN either votes for class or averages values, depending on the problem. We use K-nearest neighbors in sklearn for classification. The workflow is simple. First, we choose K, the number of neighbors. Then, we measure the distance between data points, find the nearest neighbors, let them vote, and finally make a prediction. In Python, we import the model from sklearned neighbors and create it using KNeighbors classifier. That's it, just a few lines of code to build a powerful classification model. Next, I will show you the key parameters inside KNeighbors classifier. First, n_neighbors. This is the number of neighbors, or K. By default, it's 5, which means the model looks at the 5 closest data points to decide the label. Second, the metric. This defines how distance is calculated. Common options include Minkowski, which is the default, Euclidean, the most widely used, and Manhattan distance. So in simple terms, n_neighbors controls how many points we consider, and metric defines what closest actually means. Weights. This controls how each neighbor influences the prediction. With uniform, all neighbors are treated equally. With distance, closer neighbors have more influence, which often gives more accurate results. Next, the algorithm. This determines how neighbors are searched. Options include auto, ball tree, KD tree, and brute force. The key point is that this mainly affects speed, not the final prediction. So weights control influence, and algorithm controls efficiency. This parameter, P, controls how distance is calculated in a more general way. When P equals 2, it gives us Euclidean distance, the straight line distance we commonly use. When P equals 1, it becomes Manhattan distance, which measures distance along grid-like paths. So in simple terms, P defines the type of distance calculation, which directly affects how we measure closeness between points. After building the model, here are the key methods you'll use to work with it. First, fit. This is where the model learns from the data by taking inputs X and labels Y. Next, predict. This is used to generate predictions for new data points. Then, predict_proba. This gives the probability for each possible class, which helps you understand how confident the model is. Finally, score. This evaluates the model's performance, usually by calculating accuracy on test data. So overall, the workflow is simple. Train, predict, evaluate. We will implement an example using KNN in Python. This example uses the Iris dataset, one of the most classic datasets in machine learning. It contains measurements from 3 types of iris flowers: setosa, versicolor, and virginica. Each flower is described by 4 features: sepal length, sepal width, petal length, and petal width. Using these inputs, the model learns to predict one output, the species of the flower, typically labeled as 0, 1, or 2. So the goal here is simple. Given a measurements, predict which type of flower it is. After loading Iris, I get a dictionary-like object. Inside it, there are several key parts. First, iris.data. This contains the feature values, also called X. Next, iris.target. These are the labels, or Y. I also have iris.feature_names, which tells me what each feature represents, and iris.target_names, which gives the names of the flower species. So overall, it neatly separates inputs, outputs, and their meanings, making it very easy to use for machine learning. This shows a complete KNN workflow using sklearn. First, we import the necessary libraries, including the Iris Dataset, train test split, the KNN model, and an accuracy metric. Next, we load the dataset and separate it into features, X, and labels, Y. Then, we split the data into training and testing sets. This allows us to train the model on one part and evaluate it on unseen data. After that, we create a KNN model with k equal to 3, meaning it will look at the 3 nearest neighbors. When we call fit, the model simply stores the training data, since KNN is a lazy learning algorithm. Then we use predict to generate predictions on the test set and evaluate performance using accuracy. Finally, we test the model on a new sample and it outputs the predicted flower species. When we click Run, the results show up. So this pipeline shows the full process: load, split, train, predict, and evaluate.